First, consider the direction where P is a prime. So P prime. I'm going to do kind of a group theory proof. So consider the elements such that they're their own inverse. So consider elements where x squared is equal to 1 mod P. That's equivalent to considering x squared minus 1 is equal to 0 mod P world, which is equivalent to x minus 1 times x plus 1 is equivalent to 0 mod P. But since P is a prime, that's only possible is if x is equal to 1 mod P, or the identity element, or x is equal to negative 1 mod P. So every element has a distinct inverse. So if you consider P minus 1 factorial, so it's equal to 1 times 2 times 3 times 4 times all the way up to P minus 1, which is the same as negative 1. Every element is not its own inverse. It has a distinctive inverse element. So the 2 will cancel with some element somewhere, which is an inverse. So 2 and 2 inverse will give me 1, where 2 inverse is some other element from 3 to P minus 2. So in other words, all the elements will cancel out except 1 and negative 1. And thus we have these equal to negative 1 mod P. In the other direction, so now I'm considering that P minus 1 factorial is equal to negative 1 mod P. Do proof by contradiction. Assume P is not prime. So P is equal to m and n, where neither m or n is equal to 1. And thus you've got m and n are greater than 1. And you've also got m and n strictly less than P. So, but these two elements, therefore, are in somewhere inside the range from 1 to 2 to 3 up to P minus 1. Therefore, you've got m times n is equal to 0 mod P, which implies that P minus 1 factorial is equivalent to 0 mod P. Contradiction. Therefore, P must be prime.